Morning. All right. Anything you want to talk about last lectures? Please somebody indicate that I am heard. Hi. Can you hear me? Anybody?
I hear you well.
Okay, thanks. All right. Okay, we wait a bit till some people come. The lectures the recordings will be downloadable. So there was a request and it is okay. So if it was not changed already, it will be changed soon, and you will have the option of downloading. All right, so maybe it would be good if you tell me, if you write me in chat, what is the research direction on which you are working, so that I would be able to think if I can incorporate it in the course. So I know what some of you do, but mostly I do not, so it would be helpful. All right, we wait still a little bit and then start. Thanks, David. We will speak about it. All right, so maybe we start. I see that, okay, the accumulation of people stopped. So we will consider in detail this picture which you saw. So I think I will have to erase it so that I will see. All right, so we are considering this generalized Lyapunov exponent, which in fact is a quantity from which you can learn a lot about intermittency. The thing to understand about it is that it is a property which is intermittent already for flows which do not have any intermittency of their own. So this type of picture, which you have here, where there are very small regions of initial conditions, which in fact may determine the space integrals of different properties, in fact also holds for Gaussian random flows. So I will speak about it in a moment. So intermittency is something which does not necessarily have anything to do with the Reynolds number. It is something which has to do with rare events, and they can be relevant simply because we are considering a quantity which is determined by tail of distribution, which moments of distance happen to be. So the intermittency of this quantity, when we consider average of Rk of t, comes not because the flow, not necessarily because the flow which stretches the pairs and causes the pair separation is intermittent. The intermittency of this quantity comes because we are considering by definition quantity so such that for different k, it is determined by different types of events in the system, and this is what causes this type of intermittency. So very low, well, roughly intermittency is the reference to the fact that you have some random system, and in that system, different types of averages are determined by different events. So this is very different from Gaussian statistics. In Gaussian statistics, you have main events, and they are the same events which determine different types of moments. So all moments are determined by the maximum of the distribution. All right, one moment, I'll have a look at what you're writing. Okay. All right, I'll speak a bit about droplets. I don't know if I'll have possibility to speak of deformable droplets and bubbles. Well, we'll see. Okay. All right. So let us, at this point, consider in more detail this quantity using this large deviations result, which we saw last time. So this is defined as integral over space divided by the volume of R0 to power k, which is of course simply a constant multiplicative factor. And the main thing in which we are interested is this integral of the noise of stretching rate. So you can call this quantity n sigma n, the stretching rate. So I remind you, this is time derivative of logarithm of r. So this is a good name. It is a fluctuating stretching rate, which in flow, which is turbulence experience, has strong fluctuations. However, if you speak of simple chaotic system, in the sense that it doesn't have any intermittency, you simply have some flow in phase space. These things are still true. However, you need some randomness, and you will see where. So you need, for instance, to guarantee that this type of the range of values of this integral is in principle not constrained by the evolution of sigma and n, which you can have in the system. So we will speak mostly about, well, not mostly, we'll speak about random systems. However, I would like you to think that many things of which we will speak are relevant for ordinary chaotic systems. So this is the quantity which we average about, and I'll give you a bit different, well, more detailed definition again a bit later. So here we have this x. I would like to stress this dependence on x. And then you want to study this quantity. And here you start using what is known as cumulative expansion theorem. So cumulative expansion theorem tells you that if you have average of exponential of some x, and you take logarithm of that average, then let me introduce here parameter k, which of course you can always absorb in x. Then this logarithm is given by sum of n from 1 to infinity, k to power n, maybe n will move back up here. K to power n looks a bit awkward. So let's k to power n. Yes, this looks okay. So k to power l, l factorial, and then you have what is known as cumulant moments of x. So what are cumulants? Many of you, I think, know this. Well, those who don't simply need to study this. It's a theory which I'm not going to prove here. However, I'll give you a literature where you have very simple, accessible, and good discussion. This theorem is used in many branches of physics, and it allows you to look at this function, generalized Lyapunov exponent, as simply the name which is used in our area for something which is very well known, which is known as a cumulative generating function. It's simply that apparently it was introduced in our area we give special name to a property which is in fact well known in probability theory. So I recommend to read on this the book by Ma, Statistical Physics. You need to check there are two books with similar names by the same author. This is in general a very good book. You will find there things which are not, which you will not see in any other books. There is different approach. It's very qualitative, very physical. So I recommend this book also for other things. So I'll give you some simple examples of what the cumulants are and why you want the cumulants. So simplest cumulant is second order cumulant, which you know very well. It is simply dispersion over random variable. Now, when you go to the, subscript C stands for cumulant. When you go to higher order cumulants, you need to think about it as something of this sort. So you have, you start with three different random variables, and in the end you will consider that y and z are in fact x. However, to understand it, you start with the case where the random variables are different, and you want to capture true correlation of these quantities. Now, what it means, true correlation? It means that if you consider the usual average of x, y, z, it does not necessarily, in the same way, in fact, as dispersion, it does not necessarily capture the correlation between all these three quantities. For instance, if x is independent of y and z, you will get that this is average of x times average of y times z. And this will still not be this average will be not zero. However, it will not be an indicator of any true correlation between these random variables. So similarly, you have contributions which also come from correlations of x and z and not correlations of other properties. And then you consider all different possibilities how you will get non-zero contribution into this average from lower order correlations of random variables. And in the end, you find this formula, which you have in the paper, in one of the papers which I sent you. It's called Reynolds dependence Lyapunov. For third order cumulant, you have moment. Okay, find it. We are not going to use it in any case. So, but yes, okay. But you do need to see at least definition of third order cumulant. And so you take this out, and then you have also this contribution, and then you will see that you also have twice x, y, z contribution. So, and then finally you have the definition of cumulant. So x, y, z. Now, if you want to understand why you have here a factor of 2, this is the reason is that you need to see that really kind of the contribution from x, y, z, which are completely independent. The contribution, so because this term also involves non-zero contribution from situation where x and z by themselves are also independent. So you consider all possibilities and you single them out, and then the only remaining thing is the remainder is what you call cumulant. So here it must be in fact minus. Okay. So moment. Check this. Okay. So this is the definition of cumulant, and to give you kind of why we are using it, consider the possibility that you study this type of integral, dt2, dt3, psi of t1, psi of t2, psi of t3. Now, if you had in this type of integral ordinary moment, then this would usually diverge where psi is some random process, simply because this t2 and t3 will be not restricted by anything, and the integrals simply there will be no limitation on integration domain. However, the moment you put here cumulant, you guarantee that if T2 minus T1 by absolute value is larger than correlation time, or T3 minus T1 is larger than correlation time. In all these cases, this type of average of the cumulant guarantees that this is negligible, so it decays fast. All right, so here you have this idea that cumulant captures only essential correlation between quantities. So whenever one of the variables of the time variable separates from T1 by magnitude, which is larger than correlation time, immediately there is fast decay. Okay, so this is kind of another way to think about it is that you kind of it's irreducible correlation function. Okay, so this is a name which you will also see because some correlations are simply reduced to lower order correlations. Okay, so then you need to spend some time on figuring out how the cumulants are defined so that you can capture this qualitative idea. However, for us, it's significant that you understand the qualitative significance of cumulants. These are, by definition, true correlations. Okay. So what does it mean, true correlations? We can immediately apply what, in our context, it means what we will use this type of understanding. So we will do the expansion. Now, what is significant here is that you can use, in fact, any type of averaging here. So this is completely general statement from probability theory, and you could use here space average as we do. You could use time average. You could use average over both space and time. What would change would be the values of these cumulants, of course. There would be different averaging processes involved. However, you can use the theorem in all these contexts. So if we apply it here, we find that logarithm of Rk of t average. So I'll remind that here we use space averaging over Rk of 0. And space average means that you throw at random a pair of particles in infinitesimally close particles inside the flow, and you watch them separating, and then you do it again. You throw at random somewhere in the flow the pair of particles, you watch them separating. You don't really care at which moments of time you do this, and this is our kind of, but if you do it at the same time, it is our definition. All right, so however, numerically you can do it at any times. So sometimes you have pieces of trajectories from certain times, then from other times, and you can simply combine them. There's no problem. All right, so according to this theorem, if you take this logarithm, this is logarithm of space average of this quantity, and therefore you can write that this is sum n from 1 up to infinity, k to power l over n factorial, and then you write this. This is integral from 0 up to t, dt1, dt2, dtn. So you can show that cumulants behave nicely under linear transformations. So cumulant of nth power of this term is, you can use it in the usual way. you can write L copies of this integral, which would be where you would designate the integration variables by T1, T2, and Tn, and average. So you have that this is n sigma n T1, and so forth, and sigma n Tn. And you do not forget to put that this is cumulative. Now you see immediately how useful cumulants are. So if you consider times which are much larger than the correlation time, so you take t much greater than correlation time, then you readily see that all this, and for any n, this is proportional to time t. And the reason is the same as in this discussion which we had, that we considered that if you have integral from 0 to t, dt1, dt2, psi, so I remind to you that we had this, we considered psi of t1, psi of t2. Here you use either dispersion, or which means that you use psi which has zero average. However, let me at this point write it in this way, okay? So minus psi of t1 minus times psi of t2. Then this is nothing but example of this type of quantity for order 2. So this is equal to integral from 0 to t psi of t prime dt prime square cumulative. Okay, so you already saw this case where L equals 2. So then this integral, as we proved by considering that the integral over t2 runs only over times which are in tau correlation vicinity of t1. Then we understood that this means that if time is much larger than the correlation time, this whole quantity equals time t integral from minus infinity up to infinity of psi t prime psi 0 cumulant dt prime. So here I write cumulant because you already simply to practice this notation. So cumulant is simply dispersion of this quantity. So this is what we had, and here you see that it's once you understood the idea of cumulants, it's very so you simply use the same thing. You understand that. So here the integral runs over t2, which are in tau correlation vicinity of t1, and here the integral runs at fixed t1. It runs over t2, t3 up to tn, which are again in tau correlation vicinity of t1. So by the same reasoning, at large times, much larger than the correlation time, this is this whole integral is going to be equal to. So this is approximately equal to time t integral from minus infinity up to infinity psi. Well, in this case, it's not psi, it's of course n sigma n. So you simply need to rename things. Taken at 0, and then n sigma n t1 and sigma n tn minus 1 this time, cumulant, and integration of dt1 dtn minus 1. Okay. So is this understood? Do you have any questions on this, remarks? Something is not understandable? Okay, so this is extremely useful because it shows to you immediately that, in fact, this quantity is proportional to time. Okay, so this gives us actual derivation that moments of r grow at large times exponentially. Moreover, it also gives us the formula for the exponent of growth. So you see that this cumulative expansion theorem actually does for us a lot of work which otherwise would be very hard to do, because derivation of cumulative expansion theorem is not that simple. So for those of you who studied, say, quantum field theory, there you do study a lot. You use this thing simply, it's kind of indispensable theorem there, because you make expansion in correlation functions, and well, you can do without it. It's not that you cannot, but the calculations become really much more cumbersome. So there you'd speak of irreducible correlation functions of quantum fields, and you see there that the derivation of similar logarithm there takes quite a number of pages, even in most concise books. And still you could, in fact, again there, you could shorten this discussion if they simply relied on this theory. So it's something of really wide applicability. And I think if you have some time to read about some things, it is worth it. So our end result is that this is equal to time t. So when we consider times which are much larger than correlation time, then it is equal to t times gamma of k, where gamma of k is equal to the series of cumulants. So I will do this shortening using that I'm writing on the board. By the way, if any of you does make notes of the lectures, please, I would appreciate if you could send it, because then I could possibly use it. So gamma of k then is given by this formula times all this. Okay. So let me okay, this red is gone. Okay. So this is our formula. So this is generalized Lyapunov exponent. Okay. So this or this is the quantity which is called this. So this is kind of the definition that at large times, so logarithm of this quantity divided by r3 of 0. So I need to set kind of straighten things here. It's logarithm of this, and this is t gamma of k, provided that time is much larger than the correlation. So otherwise it looks not really good. Okay. So this is this point everything is good on the board. So what we find is that essentially by definition at large times rk of t is given on average by rk at 0 times exponential of gamma k t. Now we also know something about this gamma k. We know the first two terms of this series. So we spent quite some time on discussion of Gaussian approximation to this average. So I remind to you that we started from simple thinking that this is at large times, this integral is effectively sum of large number of independent identically distributed random variables. And therefore, you can use central limit theorem and assume that it is Gaussian. And then we made the calculation of this Gaussian averaging. And our Gaussian approximation was that gamma of k in Gaussian approximation. So erase this. it is k lambda 1 plus k squared over 2. And then there was a quantity which I called mu. However, because I want that you look at the paper which I called Properties of Generalized Lyapunov Exponents, where all these things are described in detail, you can simply put here deltas to have consistent notation with what is written there. And then this is integral n sigma n at time 0 and sigma n at time t. This time I'll use this cumulant. So this is simply dispersion, but I want us to have some exercise or to train this notation. All right, so this is Gaussian approximation, and at this point you understand it much better. It simply means that you cut off all terms in the series with order which is larger than 2. And in fact, it is a good way to think about the central limit theorem, that you have often, in many cases, you can prove that some random variable is approximately Gaussian by observing that its cumulants of order higher than 2 are actually much smaller than second order cumulants, and that means that the variable is approximately Gaussian. So this is another way, another approach to central limit theorem. So we know this first two terms, they hold generally. They are simply described in the first two terms of this series. And then you see immediately that gamma of k is not at all equals to k lambda 1. There is always some correction. So it means that you cannot use the behavior, which is r of t, which is r of 0 times exponential of lambda 1t. Okay? So we will speak about it more and more, and you'll understand these things more, but we started our discussion from telling that if for each trajectory at large times this law holds, then maybe on average you will have that rk of t is exponential of gamma k t. And then in this case, if this is true, we thought that gamma of k would be k lambda 1. And you see immediately from cumulative expansion theorem that this cannot be true because there are corrections. And this would only be true if you would consider k's which are either very small, then you would be able to neglect it, or for some reason all this delta is small and also higher order cumulants are small, and then again taking k not too large, you would be able to tell that this is the limit. Now this is certainly not the case in turbulence, and there will be a constraint of which we'll speak in a moment, that for any incompressible flow, this function at k equals minus dimension of space, in our case it's d equals 3, is actually 0, which is very much different from this prediction, which would be minus 3 times lambda 1. All right, so however, we kind of gradually accumulate more and more knowledge of this quantity, and you will see these things as we progress. So this is our gamma of k, and then immediately we see that there are several properties to think about here. That once you have this representation and you realize that for turbulence, velocity gradients are strongly intermittent properties, in the sense that their statistics is very volatile and strongly non-Gaussian. And I remind to you that we had this, as we discussed, average of grad v to some power. This might be not with, no, sorry, I'll simply increase it. So average of modulus of grad v to power k, which we actually considered as average of, it would be nicer to think about it in this way. It is given by powers of Reynolds number, where epsilon tilde is nu grad v squared over epsilon average. So statistics of gradients in turbulence, which of course gradients are simply obtained by putting here instead of epsilon tilde grad v squared. So it would be the same law as for grad v to power 2k. So gradients are, their moments grow with Reynolds number in a very non-trivial way, power law which depends on the order of moments. So that intermittency must be relevant to this quantity. And it must be very relevant because each term is going to have its own power of Reynolds number at large Reynolds numbers. So you see immediately that there is something to think about whenever you study some properties below the viscous scale. Intermittency must be relevant. You need to deal with it very seriously, and if you don't, you simply can get some qualitative and quantitative mistakes. So other thing is that actually this law of growth, which is written here, allows us immediately to conclude, to make a conclusion about the distribution of stretching rates. So how do we define stretching rate? Well, average stretching rate. So let me erase this. Okay. Okay, so we consider the property which is, so we have this and large deviation theory result, which we considered previously, tells us that if you introduce lambda of t, which is 1 over t integral from 0 to t and sigma n, then dt prime, then its distribution is going to be, so this is called finite time Lyapunov exponent. We talked about this definition. It simply refers to the fact that if you consider r at time t, then according to this definition, this is r at time 0 times exponent lambda of t times t. So it gives you simply time-dependent exponent of growth, and this exponent of growth depends on x and in principle on initial orientation. I'll comment on dependence of initial orientation later. So this is kind of explains to you this quantity and its distribution at time t, at p lambda of t, has large deviation form. Okay, never mind. So it's distribution 1 over minus ch of lambda. Okay. So how do you see this result from what we studied? How do you understand that probability density function is this? So for starters, I want that you understand that this is description of this picture. So probability means, in this case, plainly fraction of space of initial conditions for which you have lambda given to the lambda of t, which is equal to a given lambda. Okay, so from what you see here, you understand that if this lambda equals lambda 1, then at large times the fraction of space of which again is definition of probability density function. It's by definition fraction of initial conditions or volume of initial conditions for which you have given value of finite time Lyapunov exponent. So at large times, fraction of space where lambda equals lambda 1 must become the whole space, it must become 1. Okay, so you conclude immediately that if this description makes any sense, then h of lambda 1 must be 0. Moreover, you understand that for all other exponents to have zero weight in the limit of infinite time, you must have that h of lambda, which is different from lambda 1, is strictly positive. All these properties will be proved, but I want us first to think qualitatively about the result. So then what it tells you is that if you consider this picture of pairs of trajectories which separate from different portions of space, then this result tells you that there is some function which, so it simply tells you that the fraction of space where finite time Lyapunov exponent equals lambda decreases in time exponentially with this weight. So let me write it because it's a simple qualitative statement, and this statement sometimes is masked by the mathematical formula, which does not reflect, might not be obvious about the physical meaning of these things. So the physical meaning is this, and it is a statement which is true for many systems, not only turbulence, which is that volume fraction of initial positions such that pairs of trajectories that issue from them. I'm not certain that you can say it in English, but I hope that at least the meaning is obvious. So that, well, maybe okay. If the sentence is not understandable, well, maybe I'll write simply in bad English, but I will be certain about the meaning. So that come from there. Decreases at large times, initial position such pairs of trajectories that come from them separate at rate lambda of t equals lambda, decreases at large times exponentially with exponent given by a certain which depends on lambda, depending on lambda. This dependence is large deviation function. This dependence is large deviations, or Kramer function, as you will see in the paper which I sent you, or entropy function, all sorts of names as we talked about it. So this dependence is large deviations function h of lambda. Okay, so if this is understood, we make a break, and then after the break we'll see how probabilistic properties of gamma of k, which is cumulative generating function, imply these properties of h. If you have any questions, please ask them in the chat. Okay, we continue. So I got a question about dispersion from Pavel. If it's independent of time, it's generally independent of, well, if you speak of this delta, which is already erased, yes, you are, it is time independent. So the integral is convergent. It was measured in a paper which I referred to previously, where the decay of dimensionless Lyapunov exponent with Reynolds number was measured. And it was also measured in the paper by Crisanti, which you have, by Crisanti et al. So it's a property which people measure, and as I told you, it's this delta is actually when you multiply it with Kolmogorov time to get a dimensionless quantity, it behaves as Reynolds to some power which is similar to 0.3. Okay, so that's the response to that question. And I'm thinking why you are wanted to know this. So let us look at the definition. Okay, so our definition of delta is that this is integral over time, integral n sigma n minus lambda 1 times at time 0 times n sigma n at time t. So this is a stretching rate, and maybe I'll introduce a notation for it at a certain point designated by psi, as we write it so often. So minus lambda 1, and this is the correlation. So this is our definition of delta. Now, you could have, the only situation where you could have a problem with this is when this integral actually diverges. Now, if you think of it, it's not so evident that it is a convergent integral. However, people measure and they find that beyond the Kolmogorov time, this type of correlation functions, here the average is over space, I remind you, and you need to have n, which already forgotten about the initial conditions. So this is steady state, well, stationary random process. So people measure it and they find that the correlation time is finite. The beyond certain time, the correlations decay fast. At the same time, you had this discussion and citation of that paper, which I sent you by Menevo and Johnson, where you see that Lyapunov exponent actually continues to change at times which are 200 Kolmogorov timescales. And they don't change much, but they change. So if you want to understand the reason for that, it might be that this quantity, in fact, at large times, it might have some non-trivial behavior. I did not see that. However, definitely our, well, not definitely, but I think that our knowledge is not completely final on this. In any case, I would not think that any problem with divergence of this integral should arise. Okay, so this is about this. If there are any other questions, please ask them, because I want to erase the board. So I hope that this picture played its role. So you can have in your mind an image of pairs well, I think you can tell is originate from different, that's the word. So pairs of trajectories which originate from different portions of space, and they have different stretching rates. So this gamma, if you see this definition, we simply, here, this is, I told you that I am doing by model for explaining things. And in this bimodal model, lambda of t takes only either the value lambda 1 or gamma, okay? In reality, all values, there's of course a continuum of possible values of lambda, and for each value you have its own decay rate, which is describable with this function, which we are going to study. So I hope that this is intuitive, simple, and there is nothing which you would not be able to understand, and whenever you need to make a calculation, well, to make a numerical simulation and to determine this quantity. So I will talk about numerical issues a little bit more later. All right, so at this point, I'll erase this. And of course, already here you observe that there is a problem in measurements. While I erase, I'll immediately talk about these numerical problems which you may have. If you want to measure moment of Rk of t, you will see in a moment that you need some lambda of t, which are significantly different from lambda 1. And therefore, they are determined by Rey regions of space, exponentially small. So this means that when doing this experiment with random distribution of pairs, you need to have really a lot of pairs in order to capture some of them to hit these rare regions and also to hit them in a statistically significant way. So you immediately see that measurement of these properties is a non-trivial matter. And in fact, it also tells you immediately that you need to be wise when you do this type of measurements, because on the one hand, you want to have large times. We are speaking about long time asymptotic regime. On the other hand, you cannot allow too large times because for large times, the fraction of initial conditions is exponentially small, decays with time. So you would need to capture enormous number of events, and it would simply exceed numerical possibilities. So you need to find something in the middle so that you can capture long-time asymptotics. You are already in long-time asymptotic regime, and yet you are not at those very large times where this simply becomes impossible because you cannot sample the volumes of initial conditions with so little fraction. Okay, so all right, let us at this point look at large deviation theorem in a bit different way, which I hope you will find many uses, and we will make a use here for speaking of statistics of dissipation. So let us look at it in a different way, which means that you are given that some quantity R of k, well, you are given this, okay? And times are large, okay? So this is t which goes to infinity in principle. Okay, so you see that you have in the moments, you have large parameter in the exponent. So the moments of some random variables behave exponentially in a large parameter. This is a situation which happens in turbulence in many cases. And you can, in fact, make a general statement. You don't need to do some kind of, it doesn't matter if this large parameter comes from large deviation theory, which means roughly that you have, you consider sums of large number of independent random variables, or maybe there's some other way in which causes some other mechanism which causes exponential dependence of moments on the large parameter. Whenever this is the case, you can claim that if you take a random variable which is logarithmic in this sense, like lambda of t, so you define lambda of t, let me rewrite this definition, it's 1 over t logarithm r of t over r0. So this is our definition of lambda of t. And you can claim that the distribution has this form. Okay, so what I want is that at this point you look at it in this way. So you don't look at this definition. You look at this in this sequence. This is the moment. They depend exponentially on large parameter, which is time. So if you define a random variable which is inverse of that large parameter times logarithm of your random variable, then the distribution of this quantity must have this form with certain function h of lambda, which, as you will see in a moment, is nothing but Legendre transform of gamma of k by the same calculation as we did already. Now, I immediately want to give you another example so that you see why I want us to think in this way and not in any other way. So if you consider the average of dissipation field, then it is given by Reynolds number to power sigma of k. This is numerical data. Okay. Now that means that if you use simply this prescription, so if you define a new variable, let's call it mu. Well, mu is maybe reserved for something else. Let's call it not so many letters sometimes. Okay, kappa. Okay, so let's call it kappa. Kappa we will not use in any other context. So if you define kappa, so the prescription here is this. You need to start from writing. So this, how come that this has exponential dependence on large parameter? You need to write it as exponent of sigma of k logarithm of Reynolds number. Okay. So this is kind of tautological. You didn't do much. However, you understand that this is logarithm. If this logarithm of Reynolds number is a large number, and this is, as I told you already, the true parameter of large Reynolds number theories is logarithm of Reynolds number, which is why we have this vast region where we're doing our simulations. Well, not me in particular, but as a community, and we're doing them at quite large number. Reynolds is truly large. We achieve sometimes 10 to power 3 in Taylor microscale, which means 10 to power 6, and we can get a bit higher. So this is really high. And yet we do not get this asymptotic regime of large Reynolds numbers. And the reason is that the parameter is logarithm of Reynolds number, and we still need to get higher. So using this logic, you need to define kappa as 1 over large parameter, which in this case is logarithm of Reynolds number. Okay. And then you need to take logarithm of the random variable. In this case, this is simply epsilon tilde. Okay. And probability density function of this kappa must then have the form which is exponential of minus large parameter, which in this case is logarithm of Reynolds number. In fact, I think in the paper it is designated by mu. Okay. So in the paper which you have on large deviations, you have it designated by mu. So please look at the papers. It's called large deviations, multifractal spectrum, something like that. And you will see the statement times some function h of mu. Okay. And of course, you can rewrite it as Reynolds number to power minus h of mu. Now, so that's the same theorem. You simply need to use it in this case. And this is kind of remarkable theorem because people are looking for probability density function of gradients or dissipation field for many years. They want to fit their data at different Reynolds numbers. You will see that there is, in fact, lots of different opinions on how you must fit, and there is apparently no unique fit for the data which is we have at our disposal. So I recommend that you read recent papers by Bodenschatz and by Srinivasan, of course, and by others. And you will see there that you have different ways of thinking about probability density functions. Now, it is kind of awkward or maybe strange that there was no observation of this form done so far. That direct consequence of this well-established experimental fact is that probability density function of this variable, which is mu, is actually given by this form. Now, with one of the people in the audience, we actually are studying this prediction, and it seems to work. So it's a very nice observation, and I hope that it will help us to understand turbulence better, because this h of mu then is interpreted as large deviations function, and then you can speak of its physical meaning, what divisions of what and why it is like that. So it's not only a quantitative result, it also brings you some stream of thoughts which you are used to from large deviation theory. All right, so then let us look at the proof. The proof is actually we did it, so there's not much to add to that. So either you do it directly, so that means that you take this equation, you study the asymptotic behavior using Laplace transform techniques, and you prove these ansatz, which can be done, or you prove it by the other way, which is in fact legitimate. You tell that, well, the solution, the asymptotic form must be unique. So if I can verify this form, then it's okay. So we don't prove the uniqueness, we take it for granted, it's true. So then you have that R, well, let me write it in this way, because our random variable is in fact R at time t divided by R at time 0. So we have exponent of gamma kt. This is approximately average of Rk of t over Rk at 0. Now, please observe that there are no prefactors here. So it's really exponent of gamma kt plus small correction in the exponent. So it's approximate equality here. Okay, it's not a proportionality or asymptotic thing. It's really approximate equality at large times. Then this, by definition, because we define in this way, then R to power k over Rk at time 0 is nothing but average of exponential of k lambda of t times t, which is by definition of probability density function integral of over lambda exponent of k lambda t, and then you use this assumption that this is minus t h of lambda. And because this is already asymptotic equality, you write here not true equality, but you write that this is asymptotically equal to this. And then you use the fact that time is large, so that this is exponential of t times maximum over lambda of k lambda minus h of lambda. And close the brackets. So from this, you see immediately that gamma of k, that you reproduce the law if you pick h of lambda as Legendre transform of gamma of k. So you have that gamma of k is, so this is definition of h of lambda. Maximum over lambda of k lambda minus h of lambda. And because gamma of k is convex, this is Hölder inequality, then you conclude that h of lambda is well defined. So Legendre transform is well defined for convex functions and is also convex. Is well defined, and due to peculiarity of definitions, in fact, it's concave. So gamma of k, one moment, I'll check. So this is gamma, no, it's the same convex. So if you define it this way, that's the same, is well defined and convex. And of course, the same thing is true for h of mu for gradients of velocity field of turbulence. All right, so this is a fact which we will use more later. I think it's really good if you have it in mind, because this situation does occur. So let us prove these properties that h of lambda 1 is 0, that h is positive at any other lambdas. Unless there are any questions. Okay. So this is our definition of h of lambda, and we must get these physical properties from that definition. All right. So let us look at this definition and then make some observations. So you start from, so you simply take different angles of view at this quantity. So if you set k equals 0, and I remind to you that what we can claim about gamma of k so far is that it is, by Herder inequality, it is a convex function, so it must be something of this sort. And I told you that we will prove later that it is 0 at k, which is -3. However, in any case, without proving this, gamma of k equals 0 is 0 simply because average of 1 is 1. So if you set in this equality k equals 0, you find that the left-hand side is 0, which gives you that maximum of h minus h lambda is 0, or in other words, h of lambda is greater equals 0. So this is already good, because if you had that h of lambda would be, that h of lambda would be negative somewhere, then of course you would run into a problem, because you would see that this exponential would simply diverge at that point. So conservation of probability necessitates this thing. So if we didn't have this inequality, we would really run into a problem. So then next thing is to show that h of lambda 1 is 0. And this is a unique 0 of the distribution, because if it would be not unique, we would have kind of two Lyapunov exponents. So Lyapunov exponent here is defined as that particular value of lambda, which volume fraction becomes 1 in the limit of infinite times. All right, so let us look closer at this definition. So when we do this maximum, we can write it in this way. So lambda, let us designate lambda at which this is maximum by lambda star, by lambda of k. So if you look for maximum of this over lambda, you take derivative, of course, and you get that this is the condition which you get. And this condition defines a function which is lambda of k. So solution of this equation is defines to you a function which is a function of k. So in other words, you can write gamma of k as k lambda of k minus h of lambda of k. And here I don't go to sometimes delicate points which need to be considered, that somewhere things can be not differentiable. This is not relevant here. It can be in other applications. So this is then a way to write this gamma of k. And direct consequence of this, of course, is that gamma prime of k is k lambda prime of k plus lambda of k minus h prime of lambda of k lambda prime of k. Now consider minimum of h. Which is the point where h prime is 0. So h prime is 0. Okay, then at that point, we have that gamma prime of k, which corresponds to that, is equal to k lambda prime of k plus lambda of k. And as usual, I get confused doing this calculation. This is really funny. Okay, so you need to set k equal 0. Yes, so you set in this k equals 0. And this is the solution. So this is holds at that k for which this is equality. And you find that k equals 0 is actually a solution from let me look. Okay, so the full proof in this paper, of course, of mine, which is properties of, so I'm getting confused in some calculation, which is, okay, so you need to use that, of course. So from this definition, you see that minimum happens at k equals 0. Okay, this is why you need to set here k equals 0, and then you need to tell that this is gamma prime. So you use that by definition. So I remind you that we had that gamma of k, which is k plus lambda 1 plus k squared delta over 2 plus k cubed and so forth. So gamma prime at 0 is of course lambda 1, which you can also verify directly from the definition. So using this, you find that lambda of k equals 0 is lambda 1, and this is the actually the unique 0 because there are no other solutions. All right, so in the end, what you find is that H has minimum, which is attained at lambda equal lambda 1. And this minimum is actually 0, as you can easily verify from these relations. So you find that we proved these equations, and please have a look more at these calculations. They're simple, but you simply need to make them carefully. It's in some sense this is the only thing which we could get, and we are simply confirming that this is true. So at this point, let us. So you understood the physical meaning of this h lambda. It counts the fraction of initial conditions. Now it's time to make an application. So I want to show to you that before we talk about properties of gamma k, which is so far we have the property that it is convex and its derivative at 0 is lambda 1. So we will derive other properties later. At this point, let us make some applications. So most immediate application is, of course, to the growth of magnetic field in conducting fluid which has 0 magnetic diffusivity. So, of course, magnetic diffusivity is never 0. And what you actually are telling is that there might be some intermediate regime in time where you can neglect the magnetic diffusivity. And indeed, there are situations when it is true. And then you can use the equation that time derivative of magnetic field. So this is called induction equation, if I didn't give you the name. So if you hear the term induction equation, this is it. And of course, you have it also in electricity itself. All right, so this is our equation, and this equation has the solution, which you can write in a way which will be useful more and more later. So it's not necessary at this point. However, I want to use it because that things will become completely obvious. So you introduce, we already had this matrix, the Lagrangian trajectories, which are defined with the help of equation of fluid particles labeled by the initial conditions. So these are trajectories for which you demand that initially they pass through X. And then you can introduce the matrix which is known sometimes as Cauchy-Green tensor. Sometimes it is known as simply Jacobi matrix because this is the way you call it for any transformations. And indeed, if you look at this, so you can think of Lagrangian trajectories as simply transformation of space. So fluid particles which were initially at X at time t are positioned at q of t and x. So this is sometimes called diffeomorphism of space. Now I'm using this term because then there is a way of thinking about flow of ideal fluid in terms of special properties of diffeomorphisms. We do not go into that discussion, but if you are interested, you can look at books of Arnold. We use this transformation in order to define simply its derivative. And because it's kind of traditionally called Jacobi matrix, I'll call it in this way. However, in literature, you can also call it, you will see also that it's called Cauchy-Green tensor. Matrix. Okay, so what is its usage? By definition, this matrix describes to you the behavior of small volumes around point X. So a small volume, you can easily see, and we will do it, is actually transformed into an ellipsoid with axes which grow as Lyapunov exponents, which we will define a bit later. And of course, by definition, you can claim that R at time t is W Tx R at time 0. So our distance between infinitesimally close fluid particles or interpair distance in this pair of trajectories which we study is writable in terms of this matrix W in this way. And you can also verify it directly. So it's kind of, so the simplest way to think of it is, of course, that R at time t is by definition distance between trajectory which originates at point x plus r of 0 and trajectory which originates at x. So if r of 0 is small, then because everything is differentiable below the viscous scale, you can approximate it with simply first term in the Taylor expansion. So this is r at 0 grad q, which is nothing but w times r at 0. Another way to verify this would be to observe that actually as a matrix, this w obeys the equation, which is dtw equals sigma w, and w at t equals 0 is identity matrix, because at t equals 0, q of tx is simply x. So this equation you can readily verify using these three equations. You take the derivative over time, and you find that this is, by simply using chain rule, you find that this equation holds. And then this gives you another way to prove this type of solution, because you see that this solution obeys that dr dt equals sigma r, which was our equation on the distance r, and also at time equals 0, it reproduces the correct initial condition. So by uniqueness of solutions of ordinary differential equations, this is the solution. Now, this way of writing is very useful in many contexts. So we will use it, and please learn it, because again, it's something which you will see quite a lot in literature. So let us start from using it for the problem of the magnetic field. Are there any questions? Because I didn't hear you for quite some time. Everything is obvious, transparent, there are no problems. You can easily follow. That's the hope. Okay, good. All right, so then let us simply write the solution of this equation in terms of this matrix W. And the solution then can be written implicitly as statement that magnetic field evaluated at the position of fluid particle is equal to W of Tx acting on B at t equal 0 x. So this is explicit, well, implicit form of solution, implicit in the sense that you consider B in the frame of fluid particle, and if you want it at fixed point in space, a Lagrangian viewpoint, then you need to make the corresponding transformation. So you can easily verify that this is a solution, and you don't really need to do it if you understood the statement that magnetic field lines are frozen in the fluid, in the flow, because this is what it expresses, that B obeys the same law as distance between infinitesimally closed trajectories, provided that initially this distance points in the direction of initial magnetic field. All right, so if you do want to verify this, you observe that this is immediately, so in the fluid particle frame, dB dt equals sigma b, and you use this equation, so you verify that it's true. Okay, so it's quite immediate way of writing, and now you can restate our result on the moments in this way. So what we found previously was that average of Rk of t divided by Rk at 0, and it is spatial average. So sometimes I forget to write it, but we all the time speak of spatial averaging. It is, using this definition, equal to average of modulus of n0 to power k. And by our result, this is exponential of gamma k t, where gamma of k is generalized Lyapunov exponent. So in other words, what we did previously tells you that space average of so dx over omega modulus of wtx acting on some initial vector to power k, and one of the brackets must be removed. Okay, this is at large times exponential of gamma kt. All right. So what we do now, and this is independent of n of 0. So the only thing is to do is to raise this equation to power k and see what it gives us. So we look at this equation, we see that if we consider modulus of this equation, we raise it to power k, we find that this integral simply equals this integral, so it must behave as exponential gamma of kt. Okay. So the last thing is that you can again make transformation of variables from x and u of t and x, use the incompressibility, so the Jacobian of this transformation is 1. And you find that usual Eulerian moments of magnetic field at time t that are defined as space average of dx over omega of b k tx must behave as exponentials of gamma kt. So you find from this that the magnetic field moments are describable with the help of generalized Lyapunov exponent, and this is one of the simplest and most transparent applications of this quantity. It shows to you that it describes a lot of physics. It's not something which is kind of artificial quantity to consider. It's really going to describe to you the moments of magnetic field. And of course, the most important of those moments is the magnetic field energy. And it's not going to be described by the lambda 1. It's going to be described by gamma of 2. So we close the circle. I told you that growth of magnetic field is not describable by the law, which is exponent of twice lambda 1t. And in fact, you see that this is what describes the difference. So generalized Lyapunov exponent allows us to speak of this type of differences. Now, it's not kind of delicate difference because, in fact, if you think of it, gamma of k is a convex function. So unless there is some degeneracy, you can write that gamma of k is convex. So, and its derivative at 0 is lambda 1. So it must be something of this sort, where this is k lambda 1. Okay? So it immediately tells you that if you consider k equal to then gamma at 2, because of convexity, is larger strictly than 2 lambda 1. The only exception would be that you have some degenerate case where gamma is simply linear. It's not the case in turbulent flow, and it will not be the case in any system which has true randomness, because there will be fluctuations of the stretching rates of this finite time Lyapunov exponent, and that would guarantee that it would not be a constant. So this constant means that actually this h of lambda is degenerate, and this PDF is simply delta of lambda minus lambda 1, which is not the case in random flows. So you find that by using not very, well, we're using very general argumentation here. We're not doing something which is beyond kind of some considerations of different properties. We simply combine the understanding of what finite correlation time brings about, and we find immediately quite a lot of conclusions. So here our physical conclusion is this, that magnetic field energy is going to grow in at rate which is larger than twice lambda 1t, despite that at large times the magnetic field grows at almost everywhere at the rate which is given by lambda 1. So it means that there would be some rare regions of space where magnetic field energy would be concentrated, and these will define this energy. So if you do some measurements in astrophysics, or you do simply simulations of induction equation, you need to think about it, because if those regions are not captured by your resolution scale, it means that you would not be able to measure b squared correctly. And of course, in this case, you don't need to make simulation of induction equation, because you know that if you have this theoretical result, you need simply to derive generalized Lyapunov exponent, and the simplest way would be to study distances, and then you would not need to think about it. However, at the moment, magnetic resistivity, magnetic diffusivity is finite, so you have in the equations of magnetic field also the term which is Laplacian. You no longer have this connection, and still it's true that magnetic field energy is concentrated in small regions of space. So this is kind of simplest context to learn some property which holds also beyond the approximation of ideal conductor where magnetic diffusivity is 0. Okay, so at this point, I want to show to you that actually we have the ability to tell quantitatively what is the volume of space where you need to watch, which you need to watch in order to find b squared, average magnetic energy. So it's nothing but this exponent lambda, fluctuating finite time Lyapunov exponent, where you need to consider what determines the second order moment of R. So we simply return to this calculation which we did previously. So average of R squared is integral d lambda exponent twice lambda t minus t h of lambda. So this is the second order moment. And it is determined by unique lambda. So this is exponent of t maximum over lambda of twice lambda minus h of lambda. So you determine lambda which solves this equation. So, and then lambda equals lambda star. So here, in fact, I'm doing something which might not be understandable what I'm doing. So what I want to show to you at this point that we can in fact get even more details from this form of large deviations, because we can actually quantitatively tell which stretching rates of which events determine the magnetic field energy. Now, what does it mean, which events? Which events means that you do some statistical average, and you need to think about it as something which is a mathematical reflection of actual procedure which you do in numerical simulations, where you simply have measurements of different events. For each event, you have the observed quantity. It has some definite value. And then you need to give to each event its probability weight, and you sum over all these over definite values times the weight, and you find the average. Okay, so this is our definition of what is the average. So because this reflects mathematically what we do in simulations, which is this picture which we had, that you have this plane where you have different rates of stretching. So at each point, the stretching is exponential lambda of tt, which depends on where you are. So we sum over initial conditions. And instead of summing over initial conditions, we tell that for each initial condition, we have some lambda, and we simply integrate over all possible lambdas with their appropriate weight. And we find that this whole space average is actually determined by very special value of lambda, because the integral turns out to be optimal value integral. And this optimal value is determined by this equation. So we might, the next thing would be to determine this function, but before we do this, we have simply from general considerations that there is a special exponent which will determine the magnetic energy. And the weight of this region, which will determine the magnetic energy, would be, its fraction is nothing but exponential of minus th of this lambda star. So for this region of initial conditions, pairs of trajectories, or equivalently, well, let's write it in this time in the language of magnetic field. So you don't need to think all the time about pairs, as I stressed. In fact, we talk about property of one trajectory. So you have some special region in space so that magnetic field grows as exponential of lambda star t. The weight, the volume fraction of this initial set of initial conditions is exponent of minus th of lambda star. And it is this region which actually determines the magnetic field energy. Moreover, we don't need to think about whether it is volume of initial conditions, because volume of initial conditions for incompressible flow equals to the volume of final conditions. So in other words, the areas in which So in order to determine at time t where the magnetic field is concentrated, you simply need to take image of this set, and its image is where magnetic energy lives. And the volume of this image is, of course, equal to the volume of initial volume because of incompressibility. So this gives you where already in Eulerian viewpoint, what is the volume fraction of which is occupied by regions which fully determine the magnetic energy in the total space. So this is a highly remarkable conclusion because you have some 3D box and you do simulation. Usual thinking of simulations is that, well, you determine some quantity, it's more or less uniform with some up to some fluctuations. However, no, it's different here. It's something which is very small region, which actually determines all the energy. So at large times, this becomes really remarkable. You have some shrinking region, which is something of, well, I will of course exaggerate, some small point from your viewpoint, and that point will contain all the magnetic energy, because when you integrate b square over space, all regions besides this one give actually negligible contribution, because here magnetic field is so strong that it actually dominates the total energy. Okay, so when you think about things in this way, you realize that we need to take cautiously lots of measurements, and we really, you really need to think about many things before you do the numerical simulation. Are there any questions on this? Okay, so then I think we need to take a break. Let's take it a break until, so for 7 minutes and 12 o'clock Spanish time, okay? We continue. So you see from these considerations that if you consider the setting a numerical simulation where you want to measure the magnetic field energy, then you need from the very beginning to think about what kind of regions are going to determine the energy. So to do so, you need to think about the form of h of lambda. You see that if you know what is h of lambda, then from this equation, you could determine what is lambda star. And from this relation, you could determine what is the volume of the regions which you need to resolve. And then say you decide that you make experiment until certain finite time t, and then you are done. You know what is the scale, what is the volume, and well, you don't know what is the scale, but you know the volume. You can also think about the scale, which you need to resolve, and with that you can already hope to get a realistic result. So how do you actually estimate this h of lambda? You see that this becomes quite crucial. Now, this is where this Gaussian approximation of which we spoke becomes very useful. So if you want to make some estimates, do this Gaussian approximation. Right, this is k, gamma of k is k lambda 1 plus delta k square over 2. And then simply do its Legendre transform to fix the corresponding h of lambda. And as you can guess, the corresponding h of lambda is also parabolic. So it's kind of necessary because, well, Legendre transform of quadratic functions is quadratic. So h of lambda is a quadratic function. You know that it has a minimum at lambda 1. So it must have a form which is lambda minus lambda 1 square. Its dimensions are the inverse time. So dimension of this is inverse time square. So as you can guess, you have something of this sort. And you only need to fix and some coefficient of order 1 in front of it. So if you know the Lyapunov exponent and the dispersion, which are quantities which are already measured, and there is no doubt that you can measure them, then you can estimate h of lambda using this equality with an appropriate proportionality constant, which is found readily. You simply do Legendre transform on this. And then you can consider this equation. So you take the derivative, you find that lambda minus lambda 1 over delta must be something like something of order 1. So because we keep only factors of order 1, I keep it here. So you find that actually lambda, from this consideration, lambda star minus lambda 1 must be of order delta. And this understanding is simple and very useful, that if you know the dispersion, you can actually, and you know lambda 1, that by definition of dispersion, so to say, you can guess what is the range of lambdas which you need to consider. So this is kind of simple. However, when you include intermittency, you realize that you get a lot of knowledge from this simple estimate, and you see how misleading the first Lyapunov exponent can be, because first Lyapunov exponent, as we saw, decays with the Reynolds number, and that we actually more or less proved that. Well, we had an inequality which shows that it cannot increase with the Reynolds number, and we showed semi-quantitatively that it decays. So we had this law that this behaves as Reynolds to power minus 0.04 at large Reynolds numbers. And at the same time, we saw that delta times tau k, that is, we take something which we take from numerical simulations, something of this sort. So if you take limit of large Reynolds numbers, it means that actually lambda 1 becomes much smaller than delta. So not large times large Reynolds number. So lambda 1 is much smaller than delta as Reynolds becomes infinite. And this is another non-trivial prediction, which means that if you do experiment at large Reynolds number of this type, of this sort, or you measure distances and infinitesimal line elements, whatever aspect of Lyapunov exponents you want to study, you discover that you need to resolve improbable array events for which the growth rate is of order delta, which is much larger than lambda 1, which means that in this equality, lambda star is simply of order delta. Okay, so it immediately tells you that when you only have in your experiments, you see that everywhere magnetic field grows roughly with exponent which is given by inverse Kolmogorov time. Now, this indicates that you see major part of space where indeed the growth is driven by lambda 1, and lambda 1, if Reynolds is at any finite Reynolds number, including astrophysical Reynolds numbers, which are up to 10 to 15, you can use this as something of order 1. So lambda 1 more or less is always of order of inverse Kolmogorov time, divided by factor of order 10, because you have the numerical thing that this is, I remind you that at Reynolds numbers, which we see in present day simulations, you have this type of estimate for the lambda 1 tau k. So it is roughly Kolmogorov time, inverse Kolmogorov time, but it's smaller by order of magnitude due to some numerical reasons, no qualitative reason for that. Besides, again, this inequality, which I showed to you, where we saw that this quantity is limited by 0.577. All right, so if you see that in most of the space, you have this growth at rate given by inverse Kolmogorov time, and you don't see any regions of space where the growth is much faster, it means that you are wrong. You cannot measure magnetic field energy in this way, and you need to make much more resolution. So this is until you see growth at the rate which is proportional to delta. So you resolve those regions. Okay, so this is some rough kind of way of getting some orientation when you don't really know this h of lambda. All right, so then we consider other application, which is to polymers. Please, when I raise from the board, think of maybe you have some remark or question. Please ask so that I can, well, at least I know that you understand what we are talking about, because I spent quite a lot of time on these details. You can find these materials in papers which I sent you, however, not everything. I give you more details here, so please ask questions if you can to make sure that you understood. All right. Probably I need to ask you some problem to hear from. Okay.
Sorry, can I ask a question?
Yes, please.
To get that average of the separation, we apply steepest descent, I guess, and so we get exponent of maximum of a function times time, but we also get divided square root of time. So is it exactly exponential, or there is some logarithmic correction? I mean, I understand that for a very long time this logarithmic correction does not matter, but for our measurements it may.
If you do, it may. So if you do this, so we have this behavior which is exponential of minus t h of lambda. Now this is not normalized distribution, and if you want to have something normalized, you need to see what is the dependence on t of the prefactor, so you consider this type of integral. Now this type of integral, because it's simply determined by the maximum of h of lambda, it's not a moment, it's probability weight, and of course probability weight is determined by lambda 1. So you get that this is roughly d lambda minus t h prime prime, not roughly, it's really that, h prime prime at lambda 1 divided by 2, lambda minus lambda 1 square, and that gives you square root of 2 pi over t h prime prime lambda 1, which actually tells you that you'd better use that p is the inverse. I hope I did not. Yes, okay. So it's t h prime prime lambda 1 divided by 2 pi exponent minus t h of lambda. So at finite times, you'd better use this to have a normalized distribution. And so this is the answer to this question of yours. What I want to stress here is that actually this is quite a good description, which you can, because if, so there can be more than that, in the sense that you could allow some slow dependence on lambda. It cannot be excluded, which in fact, let me show it where it comes from. So when we define gamma of k, we have that logarithm of r to power k is of order exponential gamma of kt. And then we did not consider the correction terms. However, there are corrections. So let us designate it by some gamma tilde of k of order, say, square root of time. Okay. This is what I remember from doing these estimates. I think you can see why it must be like that, but maybe it was a constant correction. Well, it doesn't matter. You can do it with whatever is here. So I think that maybe it was a constant correction here, so which is neglected at large times. So it gives you kind of an envelope. So you see that it depends on k, and therefore it means that there is also some slow modulation of this equation as a function of lambda, and not simply this multiplication of constant. So if you want to get more kind of more details on this, you would need to write that this is some f of lambda. You would know from this behavior that f of lambda at lambda equals lambda 1, to have good normalization, you do need that this is this factor square root of t, h prime prime, lambda 1 over 2 pi. However, it can be that when you are away from lambda 1, this function is no longer this constant, it's different, which will not produce any problem in any calculation. However, at finite times, you might need to see it, to include it. And the simplest way to do it would be probably to include corrections to these formulas, to go in the formula for gamma of k, to go beyond order t and see what happens, what corrections you get there. Because for gamma of k, you have this cumulative expansion, which actually works at all times. So maybe if you want to address really small times, you'd better start from this cumulative expansion theorem, which is true at any times. Okay, so this is the good thing about it. So you have this this integral from 0 to t, dt1, dtl of, so I designate this n sigma n with psi. So you have this integral psi of t1, psi of tl, cumulant, and then it's simply that you might work at times where this is still not proportional to time. It has some corrections which are not negligible, and then you simply need, well, not simply, but you need to work this out. You need to consider the behavior of these cumulants. Cumulants can be calculated directly from the turbulent flow, and using the behavior of these cumulants as function of different times, you can then estimate this gamma of k, and in the end, this function h of lambda is more or less only its Legendre transform, so you can then figure out its behavior, the behavior of p of lambda with no problem. So this is the approach which I would propose to do at finite time. So start with this and consider all, for given k, find out which terms in the series are relevant, because starting from some order, the terms become certainly irrelevant. This is convergent series. And for those terms which are relevant, study the behavior of cumulants and get some conclusion. Okay, any other questions?
Thank you.
You're welcome. All right, so let us then go to polymers. And while I'm erasing, please observe that cumulative expansion also gives you another way to measure this generalized Lyapunov exponent, because you can directly study the cumulants. So you take turbulent flow, you determine matrices of velocity gradients, you determine this noise psi by evolving vector n, you reach the steady state in terms of this n, and then in isotropic case, it's very simple. You simply assume that n is a randomly pointing random vector on unit sphere. It has random direction. So, well, it is correlated, it's not that easy. Okay, so you need to evolve this n to get, in a steady state, this n is pointing in a very special direction called major stretching direction. You can determine it with no problem and study then. I will speak about this major stretching direction because it's essential. And you can study this cumulants, okay? So it will not be, so maybe it will be, in fact, also more effective way to study gamma of k at large times. So, so far I proposed this way of calculation to people who do numerics, and those people with whom I spoke about, for them it was simpler to do it straightforwardly. However, I would think that as you get to larger Reynolds numbers, it might be in fact more useful to study directly the cumulants and not the time-dependent quantities, because these cumulants are simply statistical characteristics of turbulent flow, which are at large times independent of time. All right, so let us return to the problem of behavior of polymers in the turbulent flow. We have that dr dt is sigma r minus r over tau. So let us start from what this r means. So if you think of it, this matrix W actually is very useful. So you consider point X and consider some volume around this point. Let us take it as a ball. Okay? So then the image of this ball is given. Each point R is mapped to point which is WTXR. So you have, so this is the volume at time t. So this is t equals 0, this is t. And point which is at distance r from center of the ball originally is at a distance which is WTXR at time t. Okay. So this vector is this W times R. Okay, so this is what this matrix, Jacobi matrix of Cauchy-Green tensor does. Sometimes I think you can also see that Cauchy-Green tensor refers to a bit different object, which is this W transpose W, but I will not go into those details. So I will call it Jacobi matrix, then there is no ambiguity. So then you can ask, what is the image of a ball? And maybe it is a good thing to ask you, what do you think is an image of a ball under this linear transformation? Is it understood what I'm talking about? Okay, so we proceed. So we are considering Lagrangian transformation of the fluid, which means each point x at initial moment of time goes to a point which is q of tx at time t. Okay, so it's transformation of space. Each fluid particle has its destination in time t. Then we introduce this matrix W, which describes this map in the small. It describes small vicinity of initial point simply by Taylor expansion. Okay. So you consider infinitesimal ball, small ball, around the initial point x. Each point, which is a distance r from that ball, is mapped to a point which is a distance wr from image of the center at time t. And what I request that you tell me is what geometrical shape the image of the ball has. Suppose a rotated ellipsoid, pancakes. Okay, thank you. All right, so rotated ellipsoid is good. Pancakes, not necessarily so. It could be a cigar. However, it's true that both of them, cigars and pancakes, are ellipsoids. So the most general answer is that this is ellipsoid. Let me show how you find it. Well, okay, let me do it myself. Okay, so in order to determine the shape, you simply pose a certain condition on the points on the boundary. So points on the boundary. So image of boundary is boundary, okay? So points on the boundary obey that if you take inverse transformation, so if you take, you consider, so let us call this is Q of Tx. So if you take points y on the boundary, then you know that if you take y minus q of Tx, in order to determine the initial point from which this y arrived, you need to equate this to Wr. I will not write the arguments of r. So you want to know which r corresponds to this. So this must be a connection between y and r. Okay. Now, what do you know about this r? You know about this r, of course, that r square is initial radius of the ball. Let's designate it by epsilon in order to stress that we think about infinitesimal ball or ball which is sufficiently small that you can use Taylor expansion of this map. So r square is epsilon square. So this condition is guaranteeing us that this y will belong to the boundary. Now let us then determine the equation of this boundary by rewriting this as w minus 1, which acts on y minus q of Tx by modulus equals modulus of r, so it's equal to epsilon. Okay. Now, what remains is that you can, of course, rewrite it as statement that y minus q of Tx times w minus 1 transpose w minus 1 times y minus q of T and x divided by epsilon square is 1. Okay, do you recognize this equation? Who does? Pavel, do you see that this is what you proposed?
No, it seems so. Oh, yeah.
Okay, so if you want to make next steps, what you do, you can introduce, you see that this matrix W minus 1 transpose W minus 1 is a symmetric real matrix. So it means that if you designate, so designate eigenvalues of W transpose by exponential of twice rho I of T, where we assume that rho 1 greater equal rho 2 greater equal rho 3, and of course you can do it in any dimension of space. Then this equation in the eigenframe of this matrix W minus 1 transpose W minus 1, which is the same as the eigenframe of W transpose, which is its inverse. The equation becomes that y1 minus q1 of Tx, and this is of course orthogonal frame, divided by exponential twice rho1 epsilon square plus y, well, let me now continue writing it in this notation, q of t x squared divided by epsilon square exponent twice rho2 plus, okay, the camera needs to focus, one moment. Right, and the last term is, of course, the same type of thing. It's plus y3 minus q3tx, where these are components along the eigenvectors of this matrix, and they're orthogonal. So this is epsilon square exponent twice rho3 equals 1, and this is, of course, equation of ellipsoid, and it's rotated to the eigenframe of this matrix. So this is the answer which was proposed by Pavel. Now, when it's going to be the answer which was proposed by Imanol, in the case where two eigenvalues would be negative. So if, say, rho1, well, so pancake corresponds to the situation where there are two eigenvalues. In some sense, well, it's not that Imanol is wrong, okay? He probably has in mind turbulence, okay? In turbulent flow, this answer is okay, it is a pancake, okay? So if you did not consider turbulence, it could be a cigar, and people actually consider seriously the possibility of cigars because you have fluctuations. However, if you consider typical situation in turbulence, indeed, you find that exponent, so you have this behavior which is describable with so-called, well, with the whole spectrum of Lyapunov exponents. So you have a law which is constitutes a part of what is known as Oscillators Theorem, which we will actually prove in the way of physicists. So Oscillators was a Moscow mathematician who proved it in 60s, I think, or 50s, well, something like that. So that theorem tells you that in each, independently of realization, which is very similar to the statement of for the first Lyapunov exponent, this axis of the ellipsoid actually behave exponentially with fixed Lyapunov, fixed exponents, which define the spectrum of Lyapunov exponents. So lambda 1 is the first Lyapunov exponent, lambda 2 is the second Lyapunov exponent, and lambda 3 is the third Lyapunov exponent. As you can easily convince yourself, and we will see it, lambda 1, which you get this way, agrees with our definition which we used previously. And then what Imanol refers to is that for turbulence, it happens that lambda 2 is roughly lambda 1 over 4. And of course, lambda 1 is positive. Otherwise, you cannot guarantee the condition of incompressibility. So incompressibility tells us that the sum of Lyapunov exponents must be 0, because the volume of ellipsoid must be conserved, which means that the product of lengths of the axis must be conserved, which necessitates that, in fact, rho 1 plus rho 2 plus rho 3 must be 0. So it's not only true in the long time limit, it's also true at finite times. So because the sum is 0 and lambda 2 is lambda 1 over 4, you get that lambda 3 is minus 5 lambda 1 over 4, which means that in this ellipsoid, two axes grow exponentially, the axis which corresponds to λ1 and λ2, and third axis shrinks exponentially. So this is how you get this flat structure, which Immanuel referred to as pancake. And this pancake is, of course, not prepared by somebody who's not very good at geometry, because it's not going to be circular at all. This pancake is going to be rather of this type of shape, which of course doesn't tell anything about its taste, but something of this sort. Okay? So it is a pancake, but its dimensions are very different. Okay. So this is the behavior of Lagrangian transformation of fluid in small infinitesimal transformation, and it also gives us immediately an idea of behavior of polymers in turbulence. So polymer in the steady state, as we talked about, is kind of a coil. So it has this form, and this form is determined by random walk arguments. And then, so if it is in fluid at rest, it's going to coil. Then you put it into a flow, and so you somehow shape the vessel or drive the flow in any other way, and there is a flow, and this flow starts to transport this molecule as a whole, and at the same time stretch it, because local gradients cause finite velocity difference between different ends of this molecule. So roughly in equilibrium, this would be this coil is a small ball. So this type of considerations actually work, and it means that the flow would make an effort to transform this into this ellipsoidal structure or pancake structure, and it will succeed so if actual growth rate of largest axis is larger than 1 over tau, it will actually increase in this direction. At the same time, say λ2 can be, for instance, smaller than 1 over tau or larger than 1 over tau. We don't really care about it, because so the actual form of polymer, of course, cares about the relation between λ2 and 1 over tau. It can be a pancake, or if λ2 is smaller than 1 over tau, it's going to be a cigar. So in any case, it does not concern us, because in all cases, the largest linear size of the polymer molecule is uniquely determined. It's some vector r, end-to-end distance. And this is the reason, in the first place, why we can define r and consider this equation, which holds in this range, where r is much larger than size of the coil, and much smaller than total length of the polymer molecule. So, as we saw, this equation implies that time derivative of logarithm of r is given by the same psi as you have, same stretching rate as you have for pairs, minus 1 over tau. So the only change which is introduced by elasticity of polymer molecule is this minus 1 over tau. Then you want to understand what kind of distribution this would produce. I will want to give you the answer and give you how you determine it in terms of generalized Lyapunov exponent, and then it could be that the complete derivation of the answer will be provided in the next lecture already. So the answer is that probability density function of rho in the steady state has exponential tail. Here, rho is defined as logarithm of r over R coil. Okay. So how you derive it, and of course this law is equivalent to statement that P of R is proportional to R to power minus alpha minus 1. So this is law of transformation of variables. So let us assume for the moment that you know this answer and see how you can determine alpha if this is true. So you see that this is a very special steady state. It is a steady state. So let us assume that alpha is positive, which means that in fact probability density function decays in normalizable way at R, which is large, which means that most of the time the molecule is coiled. So below coil stretch transition, when the polymer is coiled, alpha is going to be positive. Okay, so do you see it? Because I see that there is some light here, but if you don't see it, tell me. All right, so how can you determine it? You realize that alpha can be interpreted as, in fact, a boundary moment. So if you accept this definition, this result, then you find that in the steady state, this is a very special steady state. So R of k is finite if k is smaller than alpha. This integral then, so you think of, let me make one more step so that it's understandable. So this is by definition R to power k, P of R, dr. And that has the property that this is finite if k is smaller than alpha, and it is infinite if k is larger than alpha. Okay. So we have a special steady state. Of course, in reality, this full length of the molecule is finite. So this means that this moment is going to be proportional to appropriate power of the total length of the molecule. However, in this approximation where we neglect that the actual length is finite, we assume that this law holds up to arbitrarily large R, you would find that this is infinite. There's nothing wrong about it. We have quite a lot of examples where probability density function, you have a steady state with moments starting from some order which are infinite. And we can use this understanding in order to determine alpha. So you observe that if you consider this equation, which I think I erased. Yes. Okay, so let me write it. So if you consider this equation, d ln r dt is psi minus 1 over tau, you conclude that r to power k at time t average is nothing but average of exponential of k integral of from 0 to t psi of t prime dt prime minus kt over tau. And because polymers elasticity simply introduces a constant into this average, we find that this is nothing but exponential of gamma of k minus k over tau times t. And here you see that moments, so k equals alpha. So to have moments with k greater than alpha growing in an unbounded way, you need that this is positive. And to have moments with k smaller than alpha to decrease and become finite, well, if, so to say by contradiction, if it's positive, it will grow indefinitely and the moment will be infinite, you must demand that gamma of alpha equals alpha over tau. So if you know generalized Lyapunov exponent, then you're actually able to determine this exponent alpha in the power law of polymer size distribution. Are there any questions on this before we finish? Because derivation of this power law is a bit lengthy. Well, it's not lengthy, but it takes more than a minute, which we have. So any remarks on this? All right, so that we finish for today. You will have the recording. Please, if you have any questions, remarks, send me by email. You don't use email at all, most of you, so you can use it. If you don't write something in the chat immediately, do it by email. Okay, thank you, and see you next time. And those in Spain or probably in Basque Country, have good holidays tomorrow. Okay. I finish. Thanks. Bye-bye.